In nitration reaction, the active electrophile forms when nitric acid is used with sulfuric acid. The active electrophile nitronium ion is being attacked. In this case, the substitution will occur at the para position because we have a tertiary carbon atom at the alkyl group. So the alkyl group has a tertiary carbon at the benzylic position, which blocks the ortho carbons. The pi bond between para and meta carbons will attack the positively charged nitrogen atom of the nitronium ion. And this is the rate determining step. Anytime benzene ring attacks the electrophile, whether it's a carbocation, nitronium, polarized chlorine, bromine, or iodonium ion, the rate determining step is formation of the valent intermediate. This is the rate determining step because in this step we lose the aromatic character of the ring, so the energy to reach this state is relatively high. We have the aromatic hydrogens that are relevant to this mechanism drawn here. Notice that the nitronium ion added to the para carbon. This carbon is now sp3 hybridized because we have a new bond between carbon and nitrogen and an existing bond between carbon and aromatic hydrogen. Carbocation in the valent intermediate is the metacarbon right here. It has 3 domains, 1, 2, and 3. Now, water that formed as a result of reaction between nitric and sulfuric acid, water will behave as base. It will deprotonate the valent intermediate, resulting in formation of the pi bond and restoration of the benzene ring. Things to consider in electrophilic aromatic substitution are the directing effects, meaning if you already have a substituent on the benzene ring, you need to find it on the reactivity and directing effects table in order to determine where the next electrophile will go. In the case of alkyl group, we know that alkyl group is weakly electron donating or releasing group, so the next substituent will go to orthocarbon as the major product, only if you do not have branching at the benzylic carbon. Let's say you have a methyl group, then the major product will be ortho. If you have a tertiary or quaternary carbon, large substituent, then the major product will be para-substituted product. Next thing to consider is the nature and structure of the electrophile. Electrophile forms in situ during electrophilic aromatic substitution, so you need to know what is the electrophile that forms when you use nitric and sulfuric acid. In case of the nitration, the active electrophile is nitronium. In case of acylation, it will be acylium ion. In case of Friedel-Crafts alkylation, it will be carbocation, and so forth. Valent intermediate is the next things to consider. What is the structure of the valent intermediate? It is really easy to confuse where the positive charge on the carbocation will be. Well, pay attention to the directing effect. If you already analyze the directing effect of the isopropyl and you know that the next group will be at the para position, then you will not have a carbocation at the para carbon because you already have a hydrogen here and you're adding one more group. So once you change hybridization from sp2 to sp3, you have 4 domains and this carbon is neutral. Therefore, the carbon next door, one that did not undergo any addition in the first step, will be the carbocation. So again, consider the structure of the valent intermediate. If the substitution will be at the para position, then the carbon next door, the metacarbon, will be the carbocation. If the substitution is at the meta position, then the positive charge will be on the carbon next door, not at the metacarbon, and so forth. Finally, once you analyze the directing effect, be sure to draw the product correctly. Sometimes you can predict the product without even drawing the mechanism. By looking at the nature of the R group, we know that the next substituent will be para, so it's easy to predict the structure of the product.